Are you live, sir?
Yes sir, chat में लिख दिया सर.
All right. So very good afternoon. Very good afternoon to all of you, my dear. A very good afternoon to all of you. So, beta, welcome to the Gate Academy English channel. And in today's session, what we are going to do? In today's session, we are going to do the most expected Gate 2022 questions. Okay. So, as we are aware that Gate examination is very near to us, and there are only 5 months are left for the Gate examination. Now, it is very important that we boost our preparation and we try to do some questions that will judge our preparation, right, my dear? So in today's session we are going to do the most expected Gate 2022 questions of the fluid mechanics, right? Most expected Gate 2022 questions of fluid mechanics, beta. So my name is Umashankar Sir, and I am a research scholar from IIT Roorkee and a faculty of the Gate Academy in Mechanical Engineering. So let's begin with the session. So we'll be having some questions, and those students who are live in this session can respond to me in the live chat, can answer to me in the live chat, and after you respond and after you solve the question, I'll be solving it. So let's see the first question. So here we go with the first question. Let's see how many of us can solve this question perfectly. Okay. I'm very confident that we can do all these questions. So please try. In today's session, we are attempting the most expected questions of fluid mechanics. Right, my dear? Can we please try these questions? I'm very sure that if we try properly, definitely we can do it. Please try it, my dear. Please try it. This is the first question on your screen. Let us see if we can do it. And those students who are live in the session, who are live in the session can tell me. Those students who are live in the session can tell me whether you are able to see it or not. Please do it, beta. Please do it. I am very sure that we can do it. Please try it. Please try it and try to respond me in the chat. Please try it. Let's see if we can do it or not. Let us see if we can do it or not. So in today's session, we are going to see some questions, most expected questions of fluid mechanics. And I'm very sure that we can do it if we try it properly. Please try it, my dear. Please try it. So I'll be giving you 3 minutes each question. Okay. And if you have not subscribed the channel yet, please do subscribe it. Please don't forget to subscribe the channel. Okay. Because we are coming up with so many videos like this in which we can solve the questions also, in which we can learn something out. Okay. So please try it. Definitely, I'm very sure that if we try it properly, we can do it. Okay. So this is the question basically of hydrostatic forces, right? This is the question of hydrostatic forces. So how we can do it? How we can do it? So do I have any answer to this question? Can we have some answer to this question, beta? Can we have some answer to this question? All right. So I'll try to do it, beta. I'll try to do it. Let's see how we can solve this question. So let me change the screen for solution. All right. Okay. Okay. So now we can see. Okay, Keshav, I am waiting, Keshav. No worries. No worries. So what question says, meanwhile, I'll read the question. The flow of water from reservoir is controlled by a 1.5 meter L-shaped gate hinged at A. So we have a hinge point, and you can observe where the hinge is as shown in the figure. If it is desired that the gate open when the water height is 3.6 meter, the mass of the required weight is. Okay, so you have to find the mass, right? We have to find the mass. All right, so what does question says? So we have a gate, flow of a water from a reservoir. Okay, what is the flow of the water? Flow of the water of the reservoir is controlled by 1.5 meter wide L-shaped gate, as you can see in this figure, hinge at point A as shown in the figure. If it is desired that the gate open when the water height is 3.6 meter, the mass of the required weight is in kg. So, Keshav, you have answered me, and your answer is correct. Very nice, but I am very impressed. Very nice. So, how we can solve this question? So, basically, we have a surface here. Let's see. So, basically, we have a surface here, my dear. We have a surface here. So, we have a surface here, and we have water. So when we know, so when a fluid is there on the surface, it exerts some hydrostatic force over it. So let's call it fx. Okay, let's call it fx. So what is this fx? We know this fx is rho g a x bar. So what is this? This is water into 9.81 into surface area. So surface area is so till what amount the water is in contact with the surface. So it is height of 3.6 and the width is given to be 1.5. So the area, always remember to take the surface area. And what is this x bar? So x bar is the distance of this centroid of the surface till where the water is present, right? So this is going to be 3.6, half of 3.6, that is 1.8. So from here you can find this fx. So now I keep telling you guys that when we have a hinge in a question, always what we have to do, we have to at some point have to take the moment about that hinge. Okay, so we have a weight here w, and we are very well aware that the weight acts upside down like this, and this is your force effect. So what is this effect? So this is your h bar, that is what we call as the center of pressure. Okay, so center of pressure, we understand that it is a point at which the horizontal force is acting, right? On which the hydrostatic force acts from the free surface. So we know this h bar. First of all, let's calculate this h bar. So we know for vertical surface it is Ig by Ax bar plus x bar. Are we aware of this formula? I am very well aware that you know this formula. So what is this Ig? So this is moment of inertia. Okay. So 1.5. So we know that it is a rectangular cross section. So BD cube by 12. Okay. So always remember to take till the point the water is present. Okay. So this is your Ig, area is 3.6 into 1.5. Okay. And X bar is 1.8 plus 1.8. Right, this is your h bar that we are getting from here, right? So when you calculate this h bar, I think we'll be getting 2.4 meter. We are getting this as 2.4 meter. So we have this h bar, okay, we have calculated this h bar. Now if we want to take the moment about this hinge point, so what we can do, so we know the moment is force into perpendicular distance. So w into 2.4 is equal to this fx into h bar. Okay, so now this is 4.5 completely, this is 3.6, so obviously it is zero point 0.9. This much is 0.9, so h bar plus 0.9, right or wrong, beta? Are we able to understand this concept? Just taking the moment about the hinge, right, beta? Right, beta? Right, beta? Okay, so now what we can do, so we have this h bar also. So h bar is 2.4 plus 0.9, 2.4 plus 0.9. So I think we are getting fx into 2.4 into 0.9, that is plus 0.9, 3.3, and this is going to be this is going to be W into 2.4. So obviously we have calculated, we can calculate the fx from here. So W can be calculated from here. And if we calculate this W, uh, we will be getting 48610. Please confirm me, are we getting the same thing or not? So when we do for mass, when we go for finding of the mass, so obviously we should divide this by 9.81. We should divide it by 9.81 and then we'll be getting the answer in kg. So when we do it, we will be getting 13365 kg, 13365 kg. So the answer to this question is 13365 kg. Always remember this tip, that if this subject, fluid mechanics or any other subject, when you see a hinge, you always prepare to take moment about that hinge. Now coming up to the second question, I hope this is clear to all of you. Now can we read this question and try to answer it? Can we try to solve this question? Can we try to solve this question, beta? Please try it. I'm very sure that we can do it. I'm very, very sure that we can do it. Very simple question, beta. Let's see if we can do it or not. Again, we have to answer it in the numerical value. So air flows through a pipe at the rate of 170 liter per second. The pipe consists of two sections of diameter. Okay, so we can't read this question, right? Okay, just one moment. Okay, because you can see me rather than. So now I think you can read this question, no? Now I think you can very well read this question. Right, beta? Same question, just because my image is coming and it is hiding up the question, so I have done this. Please try this one, beta. So we have air flows through a pipe, and do not forget to like and subscribe the channel, beta. Air flows through a pipe at a rate of 170 liter per second. The pipe consists of two sections of diameter 18 centimeter and 10 centimeter with a smooth reducing section that connects them. The pressure difference between the two pipe sections is measured by a YouTube water manometer. Neglecting frictional effect, the differential height of water between the two pipe section is. That is what we have to solve. So we know that this is a combined question. So in a gate examination, this is what we can say. This is a question of combined statics and dynamics. Both are combined here. Both are combined here. Please try solving it. I am very sure that we can solve it, beta. I am very sure that we can solve it if we try to. Very, very simple question, beta. Very, very simple question. Very, very simple question. So what this question is telling us, beta, shall I try it, my dear? Those who are live can respond to me. Those who are live can respond to me, beta. So how we can solve it? So first of all, beta, when we are solving a question, it is very, very important that you read the question well and you try to understand and always try to develop a figure for it. So air flows through a pipe at a rate of 170 liter per second. The pipe consists of two sections of diameter 18 centimeter and 10 centimeter with a smooth reducing section that connects them. Okay. The pressure difference between the two pipe sections is measured by a U-tube water manometer. Neglecting the frictional effect, the differential height of water between the two pipe sections is take density of air as this and G as this. So what we have to do, first of all, let's draw the diagram. So we have a pipe of reducing cross section and a smoothly reducing cross section. That means it is like this. Okay, it is like this. So it is of having 18 centimeters. So this is of 18 centimeter dia, and this is of 10 centimeter dia. Okay. And the pressure is measured by U-tube, pressure difference between it. So obviously when the section is reducing and there is some diametrical changes in the section, so the pressure will be different. Okay, pressure will be different. So the pressure is being measured by the U-tube manometer. So let's place a U-tube manometer. Okay, so as they are saying a U-tube manometer, sometimes people ask me, sir, why not we make the manometer on the upside? So if we make on the upside, that will be called as the what? Inverted U-tube manometer. Inverted U-tube manometer, right? So Keshav, your answer seems incorrect, beta. Let us see. So now air is flowing inside it. We have air inside it, and we have water in this manometer because it is a water manometer. So let's say that, so we know that when we are placing the manometer, okay, when we are placing the manometer, there is a difference. There is the difference of the height in between the manometer. There is difference of this column of this manometer, and this is x, my dear, and this is x, my dear. Okay, this is your x. So what is this specific gravity? So if I call it manometric fluid, and if I say the specific gravity of this manometric fluid is water, so it is 1. And for air, the specific gravity density is given to be 1.2. So let's call it the specific gravity of air. So let's call it 1.2 divided by 1000. So this is the information we are having in this question. So if I use the Bernoulli equation between, let's call it section 1 and let's call it section 2. So we very well know by Bernoulli equation we can write this way: P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus V2 square plus V2 square by 2g plus Z2. Right or wrong, beta? Can we write this way? Can we write this way? Yes, sir, we can write this way. So the datum being same, no information about the datum is given. So we consider it to be same. Okay, so ultimately we have to find this x. Okay, Keshav, we'll see to it. Okay, so now can we write P1 by rho g minus P2 by rho g is equal to V2 square by 2g minus V1 square by 2g. Can we write this way or not? Please answer me yes or no. Yes, sir. Obviously, we can write it. Obviously, we can write this way. Now, I think we very well aware of this. We are very well aware of this, that P1 by rho g minus P2 by rho g is your H. So H is what? So pressure head difference. This is your pressure head difference. We know that P by rho g is pressure head. So pressure head difference between 1 and 2, and here the density that we should use is of air. So this pressure head difference is in terms of air. In terms of air. So remember that when we are applying the Bernoulli equation, the pressure head difference that we are finding out is in terms of the fluid flowing inside the pipe, right? So air is flowing inside the pipe. So this pressure head difference is in terms of the air. So we very well know this fact that when a manometer is applied, this H is given by X Sm by S minus 1, right? Are we aware of this formula? I think we are very well aware of this formula. So placing it here, Sm by S minus 1 is equal to V2 square by 2G minus V1 square by 2G, right? And we also know that A1 V1 is equal to A2 V2 is equal to Q, right or wrong, beta? So from here we can find this V1. So V1 is Q upon A, right, beta? V1 is Q upon A1. Okay. So Q is given in the question, the charge is given in the question, that is 170 liter per second. So 170 into 10 to the power 3, 10 to the power minus 3. And what is the area of one section? So diameter is given to be 18. So pi by 4 into 0.18 whole of a square. So from here we can find the value of V1. Can somebody please tell me what is this V1 is coming out to be? Can somebody please tell me what is this V1 coming out to be? So we have this V1 as, so please cross check it. So we are getting this V1 as 6.68 meter per second. Are we getting the same or not? Are we getting it, Bida? Can you please confirm me? Very good, Keshav. And this V2, so obviously if V1 is this, so V2 is Q upon A2. So A2 is 10 centimeters. So we can find it A2 by using diameter as zero point 0.1. So basically we are going to get 21.64. 21.64 meter per second. Now, can we place the value of V1, V2, Sm as everything in this equation and get the value of x, right? Can get the value of x. Can we do that, beta? Can we do that? So if we do that, what are we getting from here? What are we getting from here? This x value. Can you please tell me, beta? So when we are placing this V1, V2 value in this equation, what are we getting? What are we getting? What are we getting, my dear? What are we getting? So I'm very sure that we can calculate it to find the right answer, right? Okay. 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 So I think this is a very, very important question, right? Because so many things we can see from here. Okay. Now here we go with the third question. Can we try it, beta? Can we please try it? Can we please try this? I think very easily we can find it, beta. Very easily we can find it. Please try to solve it, beta. Please try to solve it. I am very sure that we can find it, beta. I am very, very sure that we can find it. Please try to find it. What are we getting, beta? So when we'll be solving this last question, we'll be getting 2.54. Okay, so when you are cross-checking the answer, so you will be finding 2.54 centimeter. Okay, Keshav, your answer was exactly correct. Very nice, beta. Very nice. Okay, we can now try this one, beta. Let's try this one. I'm very sure that we can solve it. I'm very sure that we can solve it, beta. Okay, again I have to just 1 second, beta. Huh? I'll copy this one and we'll paste there. Okay, now I think you can see it perfectly, beta. Okay, now I think you can see it perfectly. Please try solving this question. Again, this is a very, very important question. According to me, I find it very important. Please try it. Let's see what we are getting from this question. So please, those who are live can respond. If there is any doubt in any question, you can please ask me. If we have the doubt in any question, you guys please ask me. Please try it, my dear. I'm very, very sure that you guys can do it. I'm very, very sure that we can do it, beta. So this is a question of fluid in motion. Please don't forget to subscribe, beta. How to do it, beta? So what this question is asking us, water flows through a pipeline whose diameter varies from 20 centimeter to 10 centimeter in a length of 10 meter. If the Darcy-Weisbach friction factor is assumed to be constant at 0.02 for the whole pipe, the head loss in friction when the pipe is flowing full with discharge of 50 liter per second. So I hope we are very well aware of this formula, a very famous formula, sir. HF is equal to FLV square by 2GD, the Darcy-Weisbach equation. The Darcy-Weisbach equation. Now, if we have a pipe, so what is given that we have a pipe of diameter, varying diameter, whose diameter varies from 20 centimeter to 10 centimeter. 20 centimeter to 10 centimeter. So we have this as 20 centimeter. We have this as 10 centimeter. And this variation happens to be in the length of 10 meter. Okay, this variation happens to be in the length of 10 meter, right, my dear? In the length of 10 meter. Okay. So now, normally when we use this formula, so the diameter must be constant. So here the diameter is not constant. So when the things are not constant and it is varying, what we must do, we must try to do it by integration. Now for integration, let me take a strip dx, and if I write that what will be the head loss due to friction in this particular length, so what we can say, fv squared dx upon 2gd. Can we write this way or not? Please answer me. Can we write this way or not? So obviously we can write this way. Now the velocity is also changing, the diameter is also changing. So what we should do, we should try to reduce the variables here, because ultimately we have to integrate it. Getting my point? Ultimately we have to integrate it. So velocity is changing, but we know that discharge always remains the constant. Okay, so when discharge is remaining the constant, just give me a moment. So discharge remains constant. So discharge is, we know, A into V. So can we write this way, that the velocity is discharge upon area? Can we write this way? I think yes, sir. Obviously, we can write this way. Discharge is Q upon area, right? Discharge is Q upon area. So area is pi by 4 d square. Area is pi by 4 d square. So what can be done? So we can write this DHF is fv square. So v instead of v, we can write q square dx upon 2g, now pi by 4 whole of a square and d square. So this is d to the power 4. Can we write this way or not? And d to the power 5 actually. Okay, so 1d is remaining here. So just place the value of v in terms of q and d square, q upon pi by 4 d square, and we will be getting this dhf like this. We will be getting this dhf like this. Yes, very good, Balaji. Your answer is exactly correct. Very nice, beta. Very nice. So this is your dhf, my dear. F q square dx upon 2g a, right, beta? 2g a square, and if we write like this, so we'll be getting this. Now, obviously, we should reduce this equation. Obviously, we should reduce this equation in terms of dx. So basically, we have to integrate in terms of dx. We have to integrate in terms of dx. So can I rewrite this equation like this? This dhf is equal to so taking the constant out, so fq square upon 2g pi by 4 square, 2g pi by 4 square, and we can write like dx upon d to the power 5, because this d is not constant and it is varying. This d is not constant and it is varying. It is varying with respect to the length. So what we have to do, so obviously this is in terms of dx. So obviously we should find this diameter in terms of x. So we have this so this is 20 centimeter, right? This is 20 and this is 10. So this is 10 and this length is 10 meter. Okay, so we want to write, so obviously we are here to integrate. So when we have to integrate, this is dx, so we should change this d, or we should find this d in terms of x. So in terms of x, if we want to find, so let's write so the diameter, let's suppose the diameter at this x section was d, where we have taken the strip, so what is this d? So what is the general rule when something is varying with respect to the some other property? So what we can say, it is decreasing. So can we write 20 minus 10 divided by length is 10 meter into x in terms of, this is the general rule of writing, right? This is the general rule of writing. How I am writing it? So I think if we call it as d1, if we call it as d2, if we call it d1, if we call it d2, so we can write d1, and since it is reducing, so d1 minus d2 upon l into x. So we can write like this. So this d, we are going to have 20 minus x, right? So this is what we have got, this d. This d, and this is in centimeter, right? This is in centimeter. Now we can place this d in this equation number 1, and we can integrate it in 0 to l. So if we integrate this in 0 to l, so we'll be having fq square upon 2g pi by 4 square, and this is 0 to l, and dx upon 20 minus x to the power 5. Now obviously by integrating it, we can find the value of, we can find the value of this head loss. Can we do the integration or not? So I'm very sure that we can integrate it and we can find the value of this HF. So when you do it, you will be getting 0.964 meters. So what is the answer to this question, beta? The answer to this question is 0.964 meters. So I hope this is fine to you. So my dear, I hope you guys have enjoyed this session and we have solved some of the questions. So I hope you guys like this video. So do not forget to subscribe it. And thank you very, very much. If there is a query, you may ask me right now. Do we have a query, beta? Do we have a query in today's session? I hope you enjoyed this session. Right, so we have solved some tricky sort of questions, right? So thank you very, very much, and please do not forget to like and subscribe the channel. So thank you very much. We'll see you soon in some other video.